Hello, everybody, and welcome to the ninth episode of the Hyperthesis podcast. Last week, we talked about the environment and a little bit about the Large Hadron Collider at CERN. But today, before we get into our main topic, I'd like to introduce myself and my friends. I'm Liam.
I'm Patrick. Hi, everyone.
And I'm Pheely.
Good to see you guys again. It's been a little while. Before we get into our main topic, though, we have some interesting news to talk about in regards to the James Webb Space Telescope. I don't know if one of you guys wants to start that.
Sure. So we've been waiting for this for quite a long time now, and I think we will definitely need a dedicated episode once some of the, science results comes out for it. But the James Webb Space Telescope, which was launched, I believe, late last year, is finally operational and has completed its testing. And just on July 12th, and I guess technically July 11th as well, they released the first images from this monster space telescope. So for those who have maybe been hiding under a rock or just not paying attention to any science news or any news feed at all, the James Webb Space Telescope has been in development for the past, I think, 30 years now, and was being built for about 20 of those years. But it's the largest space telescope meant to replace the Hubble telescope. And after many, many years, many delays, it's finally operational and it is stunning.
Well, people are still figuring out, the theories from the data from the Hubble telescope and stuff. There's so much data that had to be processed and true. And now we have a high resolution data. And I can't wait to see how many years until we process those data, because it's going to be long. And a lot of information about the James Webb Telescope, like explain how it works and stuff, you can find at NASA website, actually.
Yeah, it's really cool. You see all these images online comparing the Hubble images to the Webb images, and the amount of detail you get from the Webb ones is just a lot better. And because it's more of a, I mean, correct me if I'm wrong, but it sees further back in the past. I don't know if you can explain that. I know it's because it can see more UV light than the Hubble can, I think.
So seeing further back in the past when you look into space means that you look further, because since light can only travel so fast, the further light has to travel, the longer it takes to get to you. So if you have an object that's, say, 4 light years away, like the nearest star system, Proxima Centauri, then it will take 4 years for light to reach Earth, and so you see 4 years into the past of what happened on that star system. Now, if you have something many millions or even billions of light years away, then you're seeing what it was like millions and billions of years ago. I will also just add that the James Webb Space Telescope is an infrared detecting telescope. So it doesn't detect ultraviolet or regular visible light like the Hubble telescope did. Instead, it goes beyond red into the infrared and detects those signatures.
Yeah, sorry, I meant to correct that. I was thinking long wavelength, but for some reason I said ultraviolet, even though that's shorter wavelength. So the Hubble telescope, how old is that? Is it from like the 70s or 80s, or am I completely off there?
So the Hubble telescope was launched in 1990. So it still took decades of planning, and I believe it was actually first conceived of in the 1940s or 50s, where they had the idea for a space telescope, but it didn't actually launch until 1990. And mind you, I believe there were some delays after the Challenger incident with the space shuttle, but it did go up on a space shuttle.
Do you know if James Webb is it like a geosynchronous, or is it like floating in space? Like, the actual trajectory of it?
Yeah, so the James Webb Space Telescope is about 1 million kilometers from the Earth, and it's at a Lagrange point or a Lagrange point. So these are points, I think there are 5 of them for the Earth, where it's almost like a balancing point where they're pulled by Earth's gravity but also still orbit the sun, but it's such that it has the exact same period as the Earth going around the sun. So in the case of the James Webb Space Telescope, it is behind the Earth relative to the sun. So it's kind of blocked a little bit by the Earth, but it's in a stable point and kind of orbiting that point. So it's not really in any geosynchronous orbit in that sense, but it is stationary relative to the Earth's motion around the sun.
I heard somewhere, and again, correct me if I'm wrong, but I heard that it's in the specific Lagrange point, kind of shield it from our sun a bit behind the Earth, and that's part of its kind of design is that there's not as much light pollution from our sun. And I also heard, and again, I don't know if it's true, but I heard that it has to kind of correct itself every now and then. It has kind of thrusters on it, and as time goes on, it kind of falls out of its orbit a little, so it has to continuously correct itself every so often.
Exactly. It's in that point, but like anything in space, there are many other effects that you can't account for. See three-body problems or many-body problems. But there's also the fact that it does need to reorient itself. So if you think about this massive telescope, it doesn't look anything like a telescope, first of all. It does have a sun shield built into it, which has many, many layers of very thin material to protect it from both light from the sun as well as any incident radiation from the sun, whether it's light or otherwise. But it also has to kind of turn itself into different orientations to view different parts of the night sky. And so to do that, it uses thrusters. I think it might also have gyroscopic controls or reaction control systems that are gyroscopic based. I would have to double check that part though.
Well, to move in space, you have to use thrusters, right? And then you have to expel mass out of it. Then the field is limited. So my guess would be James Webb Telescope would have basically a lifetime that calculated. We spent so many years. I hope they put enough fuel to last more than how it's built.
So I think the initial estimate was somewhere around 10 or 12 years that would have enough fuel for, but it's NASA and they over-engineer absolutely everything they do. See the Ingenuity helicopter on Mars. But in this case, they're saying, oh yeah, there's probably 20 or 30 years worth of fuel that's packed on. And they're also interested in possible refueling, just because, like you said, this is a very heavily invested project. It seems weird to call it a project, but it is. And to be able to have it operational for as long as possible is beneficial, because who knows when NASA will have the funding to do something even better than James Webb.
Yeah, even they put so much money into the telescope. It's kind of like the modern day version of the Hubble telescope, right? Like they've been planning it for years and years and years, and it's the like if you look at you should definitely check out those comparison photos between Hubble and the James Webb. But like they just capture so much more light. So if you look at the stars in the Hubble images, they're these small little blurry dots, and if you look at them, some of them in the Webb images, they have these bright spikes coming out of them, which indicates that a lot more of the light's being collected by the Webb. And I think we talked about those in one of our previous episodes. How the James Webb Space Telescope has all these kind of hexagonal gold mirrors all on it, which I think they're coated in gold. Maybe they're not completely. Yeah, they're coated in gold. So that tells you how much. That's part of the money they put into it. But because of those hexagonal shaped mirrors, you get these diffraction spikes that we mentioned before. So when you look at the stars in the images, some of them have these huge kind of spikes coming out of them, and that's kind of due to the nature of the telescope itself.
Yeah, on the actual like images website that they publicly released, they actually have a poster explaining that phenomenon that actually comes from the two axes of the lens of the telescope. Or I haven't read it entirely, but yeah. Anyways, one evil part of me want to see maybe a little asteroid that's like on very, very low chance would hit the telescope. Like, oops. Well, but Murphy's law, Who knows?
So, fun fact about that is that it's already been hit by a micrometeoroid. Yeah, I think it's a meteoroid. But I believe it hit the mirror, and that has an effect. So every tiny bit of space dust that collides with it will cause a little bit of damage that they have to account for in these images. So over time, this is a very large surface area. And again, space is big, but there's still chances that things will run into the telescope, and they have to account for the slow accumulation of defects that will occur. Also, with the telescope, if you see images about it, those are false color images. So, like we said earlier, it's an infrared telescope, unlike Hubble, which is a visible light telescope. And so, any images that you see from James Webb that look the same as the Hubble pictures, so if you see those comparison photos, the James Webb Space Telescope has been giving color to give you the idea of what the colors are actually like based on the visible luminance from the different particles that are found. But it's all fake. But the images are real and the science is real, just the colors are fake.
Yeah, it's the same idea as an infrared camera, right? Like we can't see infrared light. When I look at somebody, they're not glowing red hot like you see in an infrared camera. That camera collects the infrared light they emit and transfers it to some visible light that we can see.
Yeah, if you think about it, it makes sense. When you look at stars in the sky, you know, the things that are bright are stars, right? Like you can't see anything else. Maybe planets. You can see some of the planets. But if you look at these telescope pictures or photos, you can see like bunch of clouds and dust. Like in itself, they don't emit light. So it's to actually see that we have to use infrared because we can see that it's emitting heat, and we try basically, well, technically it emits light in infrared, but it doesn't emit in the spectrum of visible light. So if you look at a night sky, even in a spaceship, you probably don't see those dust that probably you have to go through. Because space is very dark, and having infrared camera is, putting color to it. That's probably a good science on that.
Yeah, so the Webb telescope, it's cool. All the astronomers I know are just hyped about it because it's now they can see new things that we've never been able to see before, like we mentioned. Things that are further away which emit these longer wavelengths that the Hubble was unable to see, we can now see. So we can see further into the past. We can see these stars and bodies that are very, very far away. That light takes so long to travel to us.
Yeah, and some of that light that's reaching us is incredibly fascinating because it's a light that has passed through the atmosphere of an exoplanet. And so some of the first results from James Webb have been observations of nearby exoplanets. And we've seen the trace signatures from water in an atmosphere on another world outside of our solar system. So just from the first results of James Webb Space Telescope, we've seen water in the atmosphere on other planets around other stars. And that's just mind-blowing to me.
Yeah, that was really fast. It's been up there so short a time they've already seen that. So what other things do they plan to use it for? I know that they're using it for kind of these exoplanet searches. They're using it to see these kind of galaxies or stars or whatever that are further in the past and give you a better idea of what happened during the Big Bang, since you're seeing light that's closer to when the Big Bang happened. But is there anything else they have? I'm sure they have tons of things planned for it, but
Well, if you literally take 30 years for a project, I'm sure they have all the bases covered. Nevertheless, I feel like we're gonna get into this so long, so we should talk about this in a later episode where we actually have done more research, and also when they release more stuff about this, so we can actually analyze and have time to ponder and think about what we can do. And maybe get Patrick to quickly, briefly summarize, and we can move on to the main topic today.
Yeah. Overall, James Webb Space Telescope, major achievement in space observation and astronomy. And I think when we do discuss the James Webb Space Telescope, we'll have to get an astronomer on here to really delve into the details and find someone who knows what they're really talking about. And so if you're interested, feel free to let us know. There will be information about how to contact us later in the episode.
Well, so today's main topic is also about visuals. It's about what we see. We talk about James Webb Telescope is what we detect from outside world, but how we present it, like Patrick said, we present infrared as colors, and the people have to decide those colors. Nevertheless, in media that we see every day, we also have these kind of effects. People try to emulate physics or simulate physics in visual arts. So today we're gonna talk a little bit about maybe popular culture, popular movies, TV shows that use physics, and how we see it as scientists, as physicists, and how accurate are they? Are they trying to be precise or they're trying to be pretty? And to me, it's very fascinating how sometimes the theory behind it, or like the actual computational thing behind it, like CGI, computer graphics behind it, didn't contain true physics. Like the simulation of wave and fluids, they're not really doing molecular dynamics to figure out how each particle interact, but they trick our eyes, or they make something that's good enough that looks like it's real. So there's a lot of technology that's gone into that, and a lot of people, even physicists, mathematicians, who takes a lot of time modeling this to not be accurate, to not be precise to the truth, but to be visually acceptable.
Yeah, and another important thing is that this kind of goes hand in hand with science communication, I think, because I don't know about you guys, but movies and video games and TV shows are the reason why, and like books as well, of course, are the reason why I decided to pursue science is because there are some good movies and video games I watched and played growing up as a kid with lots of kind of sci-fi jargon thrown around and spaceships and all kinds of stuff. So the way you present things to the public can make a big difference, I think. And even a lot of our mentors, a lot of physicists that we had teaching us as undergraduate students, a lot of them got into physics because they really liked Star Trek as a kid. So it's interesting.
Yeah, I mean, like to me, I was fascinated with the Lord of the Rings was one that actually the first fantasy movie that I was like really got hooked on. Even though I didn't know much English then, so I watched it all dubbed, but the visual was just unreal, right? And I remember reading some comments about some, I think some new video games is coming out, and it's funny thing it said, oh, the book has better graphics because the new game just has very horrible 1990s graphics that's releasing soon. It's hilarious. But yeah, there's some people who just don't know how to make something that looks realistic.
Yeah, bit of a side note. I watched the first two Lord of the Rings movies last night. I still have to go through the third one, but their animation still holds up today. Like I can nitpick at it a little, but it's still pretty solid when I see it, considering it's been so long. But anyway, that's a bit of a side. We should get back to our topic at hand.
Well, there's also like visual tricks and stuff. If you look at old Star Wars, when they actually make like the all the clone soldiers and stuff, they lay over the painting on glass and you shoot through it. It's kind of like that's kind of crazy. It's very ingenious to come up with those tricks but it looks really real. Like, and then we kind of also get into like lightsabers and stuff, which in terms of as a physicist is completely ridiculous.
Well, there's some people online on YouTube that have made some as close to real life lightsabers as they can get, although they're definitely not the ones you see in the movies. But yeah, so in a lot of movies and TV shows and games, um, in terms of animation, they're not. If you have water flowing down a river, they're not solving the Navier-Stokes equations. Usually, they have a lot of very clever workarounds to kind of simulate something that looks realistic, or even light reflecting off of water in games. So like, I forget which the exact details, but like one of the Assassin's Creed games, the Black Flag one, like the water in that is pretty nice, I've heard, although I've never played it. And even in games with mirrors, so like there's games where there's bathrooms and they have mirrors in them. A lot of clever kind of thought goes into how to. A lot of games they'll just blur out the mirrors, so they're useless. But some of them they'll actually do the ray tracing and reflect it off, and then some of them they'll just to make a workaround instead of having to simulate all of the rays of light reflecting off and continuously updating it based on how you look at the mirror and the position you're in. They'll kind of just take a copy of you and put it in like a separate world that you can see into. So there's a lot of clever workarounds.
So I'm gonna section this quickly because now I think I'm gonna talk a bit about lightsabers and how ridiculous they are and what's going on with those YouTube videos. And then we can go and talk about water and how water is simulated. And then we can talk about how mirrors are simulated in video games or in computer graphics.
Well, we should also maybe mention talk about kind of science and media a little bit too. I don't know if we should start with that or end with it, or so I'll let you take the floor with the lightsabers.
Well, I haven't done much research on it, but so I'm just going off of my memory. So in my humble opinion, that when I watch Star Wars, I think of lightsabers as suspended light, right? Like they're able to trap a light into a beam. It's like you look at those fluorescent tube for your lights, the old lights that are big long cylinders. Yeah, it's kind of like that, but without the casing. You can trap lights. That's really cool. But what I saw in those videos, that actually, to me, it just looks like lightsaber, but in principle, completely different. They connect basically gas, like combustible gas, into a tube and propel it and light it up. So to me, that's not lightsaber. It's literally a flamethrower. That's very strong.
Okay. To get a little bit into the Star Wars lore, the lightsabers that we see in the movies and everything are lightsabers, but there were things before them called proto-sabers. So these were things that had, say, external battery packs or external power systems of some sort, because allegedly lightsabers take energy and maybe the use of the Force, depending on which canon you believe or not. So the videos that you might see on YouTube, I think one of the bigger channels is the Hacksmith, who has made these proto-sabers. They are technically legitimate in the Star Wars universe, where they may have existed in their initial form. Now, I know modern lightsabers use kyber crystals and whatnot, but just putting it out there that what we're seeing today is just a natural progression into lightsabers.
Yeah, that's the way to think of it. It would be quite hard to master all 7 forms of lightsaber combat with a proto saber. Like those guys on YouTube, they probably melt themselves trying to do the flips and the spins. So once we get a real lightsaber, though, I know what I'm saving up for.
Well, since those proto saber thing, they are shooting gas. When you move, the gas has inertia, so it's gonna stay there. You can't just swing it around like lightsaber. Expect nothing to stay in in the same place. So it's gonna burn a lot of things.
Okay, so there are people who thought about this. Mikio Kaku, the famous theoretical physicist, has actually put some thought into this. And so light might just be the word they use for it, but it's proposed that an actual lightsaber might be able to be built as a plasma. And so plasma is a whole bunch of charged particles or ions that are very hot. And if they're charged particles, that means you can control them with a field. So whether a magnetic field or an electric field. So if you had some sort of ceramic material up through the column of the lightsaber, much like think of those plastic lightsabers that extend, except a very high temperature conducting ceramic material that could form a plasma produced around it into essentially a lightsaber. And that's powered by some sort of futuristic battery system, then we can have actual lightsabers that are essentially just a gas that's been ionized, being held in place by magnetic or electric fields. It would, yes, be very hot and probably melt your hands, but still, it could be possible.
Well, and I also have a problem with the word lightsaber, because saber, by definition, is a curved blade. And it's like usually all lightsaber, it's not a saber. You kind of light sword, light rapier, but it's not a saber, you know? Yeah.
Well, Sir Christopher Lee, the actor for Count Dooku in Star Wars, he had a saber actually. So it's kind of funny. A lot of Star Wars lore is just they kind of just made it up as they went. Like Mace Windu's lightsaber being purple was just the actor wanting a purple lightsaber, and then they made a whole lore based around it, saying like, oh, he's on the light side, but he's got some dark side aspects in him. And so Sir Christopher Lee, the actor for Count Dooku, actually knew how to fight with like fencing style sword. So his lightsaber hilt is actually curved, and he fights in that style because the actor actually knew how. And then they just kind of they're like, oh, well, that's now a form of lightsaber combat.
Yeah, actually, like if you do fencing, I don't, but I have a friend who does. There are multiple weapons. It's not just one, just the skinny rapier you see. Yeah, there are other ones. There's one like the saber too. And I get it though. At the time when George Lucas did Star Wars and stuff, they're probably one of the first, big fantasy space movie. No, there are other ones, but they're not Star Wars. There's a reason Star Wars are Star Wars, right? And they can do whatever they want. And the thing about physics in movies are that people, for something that's new, like lightsaber, people don't see it in real life. So in a way, you have creative freedom to express it however you like, that the general public have no idea. Like if you think of lightsaber, like who has seen lightsaber in real life? Nobody. So you make up something that looks like lightsaber, that call it lightsaber, then they are lightsabers. And movie use these tricks a lot. Like you blast guns, you're shooting little beams out. I was like, well, if it's realized in real life, like the beam wouldn't just stay in like a short little beam that's visible. That's kind of weird. You might see that in photos, like when you fire like a tracer shot in guns, but that's kind of strange for just light.
That's so it's a pretty common thing in these kind of sci-fi TV shows and movies for they just kind of made stuff up which wasn't physical at all, right? Like lightsabers and laser guns, that kind of stuff. And then later in time when they were these big franchises, they sat down and said we should probably try and solidify the lore around these things. So I really like it when games and movies and like things they spend a lot of time trying to, although they have to do weird sci-fi stuff and break science to make something fun, they try and like stay as close to it as science as they can. And Star Trek did a really good job with that. Star Trek maybe not as action packed as Star Wars typically, but it's a lot more realistic, I think. In how they do things like warp drive, they use warp drive to travel across the galaxies or universes or the universe they're in, and that's an actual thing. Warp drive is theoretically possible. Now, how do you have enough energy to do that? They sweep that under the rug, but they try and come up with some explanation. And I remember I was watching an episode of Voyager with my girlfriend's dad because he's a big Trekkie, and Geordie LaForge, the chief engineer of the Voyager, got stranded on a planet, and there was these big electromagnetic storms. So the Voyager was in orbit around the planet, and he's like, I can't contact them with my my usual methods. And he sat there and he was like, oh, I'll just make a neutrino beam and fire it up to them. And I sat there and I was like, oh my god, like yeah, if assuming that you have a way to just easily make neutrinos and the ship has the technology to detect them, that's exactly what you do, because neutrinos don't interact with things very much at all, and they would just whiz right through that storm straight to the Voyager. So I really like when franchises try to do their best to keep things scientifically accurate, although they still have to kind of, in the end, they have to ignore it usually.
Well, one thing about warp drive to me is not about the energy, but how do you find the negative mass
Well,
to create that warp drive? That to me is fascinating.
mhm.
And also like the neutrino beam thing was actually people who work at the Snow Lab, they try to find they create neutrinos and stuff. I think was approached by the U.S. military to potential way to communicate secretly and stuff. It's kind of hilarious. Like, wow, you're gonna build a detector that costs you so much millions of dollars just to detect this tiny thing to encode secret messages. That's interesting.
Yeah, that'd be really funny. Like trying to come up with a secret way to send messages with neutrinos. It'd be like, all right, I'm gonna fire this message in your general direction for the next month, and hopefully you receive like a tiny little signal at some point.
Yeah, someone who has worked on detectors and worked with people who work on neutrino detectors, it's ridiculously difficult to actually detect neutrinos, and it's so rare. Like I remember when Arthur McDonald came to visit our school, he said that a massive supernova happened not too far away, and from that event where just an unfathomable amount of neutrinos were produced, 13 interacted with the Snow Lab detector, which, mind you, is massive in itself. So that's quite silly of the U.S. military.
Yeah, for a reference point. Well, first off, Arthur McDonald, the Nobel Prize winner from Canada, which is nice. And he basically showed that neutrinos have mass, so they're not massless particles like light. But for reference, neutrinos do not interact with things. I mean, they do, but very, very rarely. I think it's like if you have like a piece of lead that's a light year long, so it's as long as it takes light to travel in a year, which is very, very far. I forget what it is in meters, but a neutrino has a 50% chance if it passes from one end of that lead brick to the other that's a light year long. I think it has like a 50-ish% chance of actually being stopped by the lead. And lead is known to stop a lot of things. You use it to stop radioactive particles in certain scenarios.
If you want to find more about particle interactions and rare events, you should listen to our previous episode where we discuss dark matter detectors.
Yes, I agree. Another thing is that the sun emits just a bucket load of neutrinos. So I think there's something like a few billion neutrinos going through the surface area of your fingernail every second or something like that. So they're passing through you at all times, but luckily they don't interact with you, or else it would probably hurt.
Well, you don't feel it. It's okay. Yeah.
Yeah.
There's a lot of things that pass through it. So to move on a little bit, let's talk about the simulation of fluids. So in fluids, for scientists, cover both air and liquids, like both gas and liquids. That's what fluids encompass. But fluids in computer graphics seems to be not very well. Like Liam said before, they didn't solve the Navier-Stokes equation because that would take forever. And people who do what we call CFD, computational fluid dynamics, they do that. They try to basically solve Navier-Stokes equation or modify Navier-Stokes equation so that you have accurate description of turbulence. That actually a very interesting and complicated area of research where some people believe that it's as complicated or even more complicated than quantum mechanics. A lot of people would frown upon that, but some people believe it. But in terms of um, simulations in computer graphics, they're not doing that. I'm curious to find out like what actual equations going on because like Liam mentioned Assassin's Creed, when they have water, I'm pretty sure those graphics are pre-baked, so they already calculated what it would look like, and they just baked it into the geometry, and maybe some rules when the ship passed, just they're all basically already calculated, not live calculations.
Yeah, I think you're right for that specific case of Assassin's Creed. And I think a lot of games, the way they handle fluid video games, the way they handle fluids or swimming is they kind of just make you float around in it, and then they create some waves that come out, but they're usually not very accurate because, yeah, I would agree that the Navier-Stokes equations are generally harder to solve than in quantum mechanics. You solve Schrodinger equations, and there's a whole bunch of different Schrodinger equations for different scenarios, and it's the same thing with the Navier-Stokes equations. And very few of the Navier-Stokes equations can actually be solved. It's a huge area of research trying to solve them, and I don't even mean analytically. I don't mean, you get an equation y equals mx plus b out of it. I mean, like, you do it numerically, and you get these kind of plots that tell you what's going on.
I wonder if you can do like, the series solutions, but the like approximations. Like, well, these are the very rough series solutions that kind of work because they don't have to simulate turbulence and stuff. They just see how wave propagate and how they like the interference patterns and stuff are pretty fleshed out. So when you combine mechanical wave, those can be done. And then my guess is also, well, I did a little bit of like try to simulate water before. You can add certain type of noise onto basically a flat surface to kind of simulate what it would look like if like kind of like random-ish noise with certain criteria to basically simulate how water would basically interact with one another randomly. Yeah.
Yeah, I think the way most video games deal with it, like you said, is the kind of pre-baked stuff where if you throw an object in water, it's like a predetermined splash occurs from it, or maybe like one of so many predetermined splashes. And even in like Elder Scrolls games, like Skyrim, for example, I'm not 100% sure how they do it, but the way it looks to me is that they just, if they're swimming through water or something falls in the water, it just emits a spherical surface wave, which probably isn't that hard to simulate because you're not actually like moving the water. The water kind of stays flat with this kind of surface wave on top of it. So as you swim through the water, it emits all these spherical waves out of you, and they kind of add up to give you like a cone shape, kind of like a sonic boom ish, like what a sonic boom looks like. But they're not physically accurate. But they're it's like a clever workaround to look like when you swim through water, waves are emitted, but it's not really the right thing. But it works for the purpose of the game.
Yeah. I know older games like that definitely have pre-programmed interactions and visuals. But I know newer games, they actually are essentially physics simulations. So they may not be having as many particles as, say, an actual ocean of water, but they're still seeing how particles with certain properties interact with, say, character or some sort of object moving through, and they're able to simulate that live. And that's all thanks to the more powerful GPUs that are coming out being able to make those calculations quite quickly. And then you combine that with the ray tracing that goes through the water, because with those particles having those physical properties of how they interact, they also have properties of how they interact with light. And so you just get this complex but legitimate simulation. And so really the thing that you need to bake into that type of code is what the particle properties are.
Yeah, about those, like I'm excited when like to hear about Unreal Engine 5. They have so many technologies to actually like simulate physics or even tricks our eyes. Like when Patrick said that they have many particles, but they're not real particles. They're like, well, I think they call it the nanite technology, where they have like a bunch of triangles, like the polygons, but they are dynamical polygons. When the closer you get to the material, the more polygon it shows. But when you're far apart, you don't need to render as many polygons, and they're actually very clever to do it. So it makes a very realistic texture and stuff, to the point that honestly, if you take a screenshot of that, I couldn't tell sometimes is it real texture or is it like a photo or it's a part of the video games. I'm not sure about the water simulation in that, and I think they have the light simulation, the lumens, maybe what it's called. I'm not quite sure what it's called, but yeah, that's fascinating how they do like a second surface interaction where it bounce and bounce again and bounce again, and just fascinating how texture interact, and I'm not sure how they do it live, real time. It was unheard of, 10 years ago to make like a animation movies with realistic lighting that take days to render, like 10 seconds. Now it's real time.
Yeah, I think just touching on the fact that animated movies themselves, at some point, the water has become indistinguishable from real water. One of my favorite examples is with Pixar. I think it was one of their short films, Piper, where that was where they introduced their new water simulation. And mind you, it takes several hours to compute each frame, but it's an actual physics simulation of water that they use in the movie. And that was, 10 years ago, even more? And now it's to the point where in movies, it's most likely indistinguishable from actual water. Whereas before, like, I think of the movie 2012, where you can tell it's fake water. It has pretty good motion, but how the light interacts with it and everything is still in that kind of uncanny valley where it's, okay, this isn't quite real, but it looks real. And now we have Pixar movies, for example, where you can't, aside from the characters and some of the background, you can't tell that it's not real, which is scary but very cool.
Yeah, movies especially. So like ray tracing in games, it's real time now, and they're just doing kind of geometrical optics, and it's wild how they can model like all the rays coming in and how they reflect and how many times they bounce off things and the caustics they form and all that stuff. Like if they go through glasses and things, but movies are really cool because they can pre-render things. So in a lot of modern movies, like Pixar movies, for example, they use like real physics for water and for other things. And even in so one example I really think was cool is the movie Brave. Is that a Pixar movie? I think so, right? Yeah.
Yes.
So the main character, I completely forget her name now because I haven't seen it since it came out. But her hair is very curly, and they spent a lot of time. They did the physics of her hair. They put in some spring constants and it jiggles a certain way. And it took them a long time to get it right because sometimes it was too jiggly and it would fly everywhere. Sometimes it was too heavy and it just draped. Sometimes they got like intertangled and then just numerical noise like screwed everything up. So they do a lot of weird physics in they do a lot of physics in weird situations you might not think they would, like how to model hair flowing or someone's outfit as they walk, or if they fall into something soft, how that bends around them. In movies they can do a lot of stuff like that, and I really appreciate it when people put time into trying to make kind of things as accurate as they can because you notice it. If something's not right, like you said in the movie 2012, even when you look at the water in it, it looks good, but something in your mind knows it's not quite right because of the way light's reflecting off of it. Even if you don't initially realize it, you kind of have this feeling. You're like, something's not right here.
Yeah, I was gonna mention too that's like apart from water, the other hard one is hair. Hair is very difficult. Even the triple A games right now, you can see hair flow nicely, but to it clips, so it go through like the shoulders sometimes. It's really hard to um basically mask it off or do the collision properly and stuff. Like I think because in movies you don't have to do it in real time. It's much more forgiving that you can sometimes manually go fix every frame and whatnot, and that's why you can see big movies got shot like a year before, like a two before it got released. It takes like a year or so just do a CGI every frame meticulously simulate everything.
And speaking of movies where there's meticulous simulation and it took a while to do simulations, I think Interstellar is an excellent example of this because of the fact that they literally simulated a black hole based on the real physics. And I think they published a paper about it too. So they worked with Kip Thorne, who recently won the Nobel Prize for his work with relativity and black holes. And they were able to build this simulation that they then beautified because, again, it's movies. You can't have just a black blob in the middle. It's got to be interesting. But it's fascinating to see how, okay, we went from, okay, hand-drawn CGI kind of thing 30, 40 years ago, think in Star Wars, to where we're simulating these extremely complex systems, not just water or hair, but many, many things, explosions and black holes, and just how incredible, one, the processing power is of these computers that they're using, but that we're able to do it and make it look good.
Yeah, it's wild. So I think there were 3 papers published on that black hole simulation. So the black hole in Interstellar, it looks like a real black hole would. Specifically, all the light that's kind of around it. And there's a good video that I saw online the other day that Kip Thorne himself, he's giving a presentation somewhere, and he basically says, "Here's the interstellar black hole," which they actually, simulated using Einstein's equations, and it was actually a really cool thing because it was kind of one of the first times that physicists had access to this Hollywood level of money to make like a good black hole simulation. So the physicists were excited about it because they were like, "Oh, we can throw thousands and millions of dollars into just simulating a black hole, which they normally can't." But he compared. You look at the black hole from Interstellar, it has this big ring around it, right? And that's a physical thing, that accretion disk, I think it's called. And then you look at these blurry orange images of black holes that were released fairly recently by these radio telescope observations, and he says, well, they clearly don't look the same. So how are they the same? And he had this really nice slides of like comparing the two, and they're actually, it's just a very low resolution image of the simulation, effectively.
Yeah, I mean, these are interesting stuff. I feel like this is gonna be a 2-part episode because I think there's a lot of things that we gloss over that could be more fleshed out in the next episode. I think that would be great because I know we have some notes down about other things that we haven't touched on at all and have fascinating physics or what ostensible physics on it. But to wrap this up, because we're gonna run out of time soon, so we have this very interesting way that people either tricks to use to simulate visual physics, or the actual simulation in physics that we see in modern media and just keep getting better and better and better. So I'm excited to see what's gonna happen in the next 10 years or even 5 years. What's gonna happen with the better hardware that we're gonna have for more accessible hardware. Nevertheless, so we're gonna get to the story part, and Patrick's gonna be talking about how we start observing sky, because we started with the little story of a news about the James Webb observation uh, from the James Webb Space Telescope. But how do humans, in general, how we as humans observe the sky from the past? And before that, Patrick gonna be talking about how to contact and reach us. You want to take it away, Patrick?
Absolutely. So if you are interested in contacting us in any way, feel free to find us on Instagram. We are at the Hyperthesis, or you can send us an email on at hyperthesispodcast@gmail.com. So reach out to us if you have any ideas for topics you'd like us to discuss, or if you'd like to be a guest on our show. We are definitely interested in getting an astronomer on our show, especially someone who has worked with the James Webb Space Telescope data, or who will be. So if you're that person and want to be a guest on our show, please let us know. You can find our podcast on many different podcast platforms. We're based at anchor.fm/hyperthesis, and we're found on Spotify, Google Podcast, and Apple Podcast. We can also join your RSS feed for those of you that do it. So feel free to find us, and we are the Hyperthesis Podcast on all of those platforms. So getting into the story, as Pheely mentioned, we are going to be going through a bit of a history of observing the sky. So with the exciting news of the James Webb Space Telescope and this monumental achievement of sky observation, I think it's important that we go over the history that led up to this moment. So before humans were using telescopes or even really making accurate records of the sky, there were still written observations of the sky as long ago as 2,000 years. So around 1000 BCE, that we have a record of people from Mesopotamia. So that's the area, I believe it's Iran, Iraq, that kind of area where civilization and especially agriculture grew significantly. We start seeing evidence that people were recording what they saw in the sky. And so these recordings were later refined by the Greeks. So the Greeks, we know, were very prevalent in astronomy. We have many of the constellation names that we still use today are originating from the Greeks. And the Greeks also had a lot of great philosophers who thought about what is in the universe, how does it work, how do the planets move, how do the stars move. And so from these questions, we had a couple different ideas occur that we still use today in star observation. So one of those first ideas was trying to calculate distance to the stars. So if you've looked up and seen the night sky, whether you're in a big city and you just see a couple stars, or you're in the middle of nowhere, like we were fortunate enough to be in Nova Scotia, and you could see thousands of stars, a question might occur to you is, how far are these away? And so Aristarchus attempted to measure the distance between our nearest star and the Earth, which is our sun. And he just tried to do that relative to the moon based on how they moved relative to each other. And so he said, I think it was about 4 or 5 times further away from us than the moon. Now, realistically, it's, I think, 400 or 500 times further than the moon. But this was a good start in trying to calculate distances and really recording down what they were observing about the sky. The Greeks also introduced a few other ideas that we still use today, such as the magnitude system of stars and celestial objects. So this is how we determine their brightness, with a higher magnitude being dimmer and a lower magnitude being brighter in the sky. So that was introduced 2,000, 3,000 years ago, and it's still something that's used today. Now, as time progressed, we began to see a shift in astronomy from European-centric to more East.
Why? That seems bad. Like, why is brighter lower magnitude? What is it a magnitude of? Shouldn't it be brighter is a bigger magnitude, not as bright's a lower magnitude? Is it just a convention?
I couldn't tell you, but if you're an astronomer that knows, want to be on the show, let us know. But I'm not sure why it's that convention
It's
specifically.
probably just a convention then. Like, it's the same thing with current. Current's defined as the flow of positive charge, even though it's carried by electrons. It's just way back in the day someone defined it. We've just stuck with it.
Yeah, probably. I mean, this was 2,000-3,000 years ago, so that they were bound to get some things incorrect. But who knows how it's morphed and changed today? I'm sure people do know. So again, if you like to let us know, we will definitely add it into a future episode. But moving on from the Greeks and their contributions and going east, during the Dark Ages in Europe, there wasn't much progress in observing the sky, aside from navigation. But Arabic and Asian nations and areas began to advance the development of sky observation techniques. So, for example, the Arabians were able to develop a better way to actually measure the angle from the horizon and the position of stars in the sky. And they were able to do this through the development of a piece of equipment known as a sextant. And so a sextant was something that was used for many centuries later for navigation. But it was because of these Arab scholars' desire to better understand the position of stars that we developed some of the first advanced methods of observing the sky. So later on, during the European Renaissance, so after the Black Plague had ravaged and we see an increase in art and music and other contributions from Europe, there were also major contributions to sky observation. So many famous names that we've discussed before, such as Tycho Brahe, as well as Copernicus, were alive during this time and were making contributions to the area of sky observation that really helped advance our thinking. So Copernicus is well known for his suggestion of the heliocentric model. I should note that the idea of a sun-centered model of the solar system had been around since the ancient Greeks, but was still debated whether the sun or the earth was at the center of the solar system and possibly the universe. But Copernicus was able to provide very good evidence that the sun was at the center of the solar system, and that is one thing he's well known for. During that time, we also had Galileo, who was able to improve upon the telescope to the point where he could actually observe different astronomical bodies, such as Jupiter and its moons, or the rings of Saturn, and he made very detailed notes about it during this time. Just a quick side note, Galileo was under house arrest from the Catholic Church, but it's not as bad as it sounds, considering he lived in a mansion and could still, for the most part, move freely just under control of the Catholic Church. But these ideas that they produced and the equipment that they produced were groundbreaking, especially the telescope. And along with the laws later introduced by Newton and Kepler, it was pretty well known how the solar system was positioned, so with planets orbiting the sun. And it also became less controversial about the dynamics of celestial bodies. So with Newton's and Kepler's equations, we could now better understand how bodies within space move around each other. So this gave us the idea that, hey, maybe the sun isn't the center of the universe and that actually orbits the Milky Way, which we now know is true. So there was a lot of good advancements and development in sky and space observation that kept increasing over time as lenses got better. So telescopes use lenses for the most part, especially refracting telescopes. And so these became more advanced and we could see better. So we could see the planets better, see their colors and textures and stripes. And we could also make better observations with stars. So these included trying to measure distances to stars based on how they moved while the Earth moved. So this is something known as parallax. So for example, if you stand close to an object and close one eye, it looks like a different angle than if you close the other eye. So you can see kind of different angles of the same object. And from that, we can calculate distances to stars that are reasonably close. So these advancements in telescopes and methods in which to measure stars allowed us to advance our star catalogs. And with these advancements in telescopes came another major milestone, which is the introduction of photography. So in the mid to late 1800s, photographs became good enough that we could actually start attaching cameras to telescopes and letting them record data. So now we could actually record the data instead of just writing it down or trying to copy it. And that lets us do further analysis and has led to the discovery of dark matter and different astronomical bodies, such as other galaxies that we might not be able to see with the naked eye. And so the continued advancement of photography and afterwards digital photography led to the idea of, oh, well, we want to remove this giant thing that's the atmosphere that interferes with our pictures. It adds noise and it changes the light in a way that makes it more difficult to actually get a solid, say, image of stars or galaxies. And so with digital photography, that would allow us to actually send a telescope up into space. And so with advancements in digital photography, as well as better optics and better uses of mirrored and lensed telescopes, we finally were able to produce space telescopes, most notably the Hubble Space Telescope. As we mentioned earlier, it was launched in 1990 and was delayed a bit. But already from the launch of the Hubble, they were discussing alternatives to or successors to the Hubble. And now we have the James Webb Space Telescope, which is the largest space telescope and really a large telescope overall that is producing these incredible images and really looking at the sky in depth.
So what's the successor of the James Webb Telescope going to be like then? I'm sure people are thinking about that already.
I'm sure they are, and I guess that's to be decided eventually. And with that, I will end the story with encouraging you to go look at images from the James Webb Space Telescope. And I really hope these images and the news that surrounds it encourages people to become more interested in astronomy. But for now, we will end the episode with that. So, thank you very much for joining episode 9 of the Hyperthesis. We will see you for 10th episode next week. Stay tuned next week for the next episode. Thank you for joining us.
Peace.
Take care.
Bye, everyone.